or I ended up in the last part describing most of the processes that are involved with generic models, and I'm about to engage on the second leg of this presentation, which involves subject-specific modeling and modeling pertaining geometry, movement, forces, and finite element analysis or properties, material properties in the hip, knee, and ankle. So the next logical question is, what is actually a subject-specific model? Well, there are 5 categories that we typically chase after. It's bone geometry, it's segmented mass and inertial properties. So sometimes when we so for example, bone geometry comes from an MRI, but if you delineate the circumference of the leg, you can add that to the model as well. So you can get the volume of the thigh, the volume of the shank, the volume of your waist, and with some approximation you can get slightly better inertial properties, even though we noticed that on the output itself, so on the moments, it doesn't influence that much. But it's typically something we like to do. Then joint articular mechanisms, that's something I have to explain, because you can have a knee acting as a hinge joint, so just flexion extension. But if you want the knee to be fully in full effect in all degrees of freedom, so 3 degrees of translation and 3 degrees of rotation, then we do that in a separate process that we call joint articular mechanisms, where we add, let's say, ligament that is involved. And we add, so we describe those ligaments as constraints, and then again we optimize the movement within those constraints and try to explain as much of the experimental gathered movement that we got from motion capture. So I got a couple of nice examples of this as well. We typically want to represent accurately muscle geometry